Okay. In this video, we will be looking at amides. Now, amides can be formed from a carboxylic acid and an amine. So if we start with a carboxylic acid, we react that in the presence of an amine, then the first thing that will happen is this amine will act as a base and pull the proton off the carboxylic acid. So we'll get a carboxylate ion and an ammonium ion. Then if we heat this mixture, so we have to boil all the water away and then continue heating it, we can actually get these two ions to react to form the amide. And the mechanism for this reaction is that, again, start with the carboxylic acid. We add the amine. The amine will deprotonate the carboxylic acid. Forming the carboxylate and the ammonium ion. So once we apply heat to the reaction, then we'll actually get this reaction to reverse. So the carboxylic acid will attack one of these protons on the amine to reform the carboxylic acid. Once we've reformed the carboxylic acid in the original amine, then that amine can attack the carbonyl of the carboxylic acid, forming this intermediate. Then there'll be proton transfer reactions that occur where this negatively charged oxygen will pick up a proton from the another ammonium ion, and then another amine can deprotonate the nitrogen forming this intermediate. Hold on, I've protonated the wrong hydroxyl, the wrong oxygen. Let's protonate this oxygen instead, producing water as our good leaving group. The electrons from our negatively charged oxygen then can come down and kick off that water, forming our amide. So this mechanism works. It's one way of producing amides from carboxylic acids and amines, but because of the high heat required in order to make this reaction occur, then it's a very harsh condition, and it will actually end up reducing the yield a lot of times. And so we need milder conditions in order to prepare most amides in good yield. And one way of doing that is using a chemical called DCC in order to facilitate the reaction. And so it will still make the amide, but it will do it under much milder conditions. In DCC, is this molecule here with two cyclohexyl groups attached to a diimide. This N double bond C double bond N. So this is DCC. And we won't go into the mechanism of how the DCC helps with the amide formation. I believe it's in the book. So amides can be hydrolyzed in two ways, similarly to esters, except the hydrolysis of amides occurs more slowly than it does for esters, and more heat will be required. Well, we can break down our amide into a carboxylic acid and an amine using either acidic conditions and heat, or basic conditions and heat. Should point out that under acidic conditions, our amine will be protonated and positively charged. So we'll go over the mechanisms for each hydrolysis, the acid catalyzed first and then the base catalyzed hydrolysis. So in the acid catalyzed mechanism, we'll begin by protonating the amide on our carbonyl oxygen. Then water can attack that carbonyl carbon, kick the electrons up to that oxygen, and then we have a proton transfer step where we deprotonate that water group and protonate our amine group. Forming this intermediate. Once we have this intermediate, then the electrons from one of these hydroxyls can come down and kick off the protonated amine, forming this protonated carboxylic acid, which we can deprotonate to form the carboxylic acid. And so in this step, we'll kick off the amine, and so we'll produce an amine and a carboxylic acid from the amide. Now we'll go over the base catalyzed mechanism. And we'll start with the hydroxyl group that attacks that carbonyl carbon, kicks the electrons up to that oxygen, forming this tetrahedral intermediate. The electrons from this oxygen can come back down and kick off this amine forming a carboxylic acid and a negatively charged nitrogen atom. So this the lone pair of electrons from this nitrogen can then attack the carboxylic acid, picking up a proton, forming our carboxylate ion plus our amine. And so this is the base catalyzed mechanism for amide hydrolysis. That we begin with the nucleophilic attack from the hydroxide ion hitting that carbonyl carbon, kicking the electrons up. The electrons come back down, kick off this amine as a negatively charged leaving group. That negatively charged leaving group will then pick up a proton, creating a negatively charged carboxylate ion and a neutral amine. So another reaction that amides will go through, similar to esters, is instead of transesterification, we have transamidation. And in transamidation reactions, you take one amide, you dissolve that with a different amine, and we produce a different amide. That we exchange these amine groups. However, while this is possible, it tends not to be particularly useful for converting one amide into another amide. So we'll look at the next set of reactions we can do with amides, and that's the reduction of amides. And the reduction of amides will be similar to the reduction of esters. Again, we start with the amide. If we were to try to use sodium borohydride, there would be no reaction. Sodium borohydride is not a strong enough reducing agent to reduce the amide. If we used lithium aluminum hydride in diethyl ether, followed by water, we can reduce the amide to the amine. Or we could use one equivalent of dibol H, or the lithium aluminum tritert butoxyhydride, followed by water to produce the aldehyde. And so we can convert amides to aldehydes by using a milder reducing agent like dibol H. Or similar to how we can convert esters to alcohols with lithium aluminum hydride, we can convert amides to amines with lithium aluminum hydride. And also similar to how esters can form cyclic esters or lactones, there are cyclic amides, which are also called lactams. And the most common lactams that we'll see are the four-membered lactams, which are called beta-lactams because of, this would be the alpha carbon and the beta carbon relative to that carbonyl. So this becomes the beta-lactam. Or we could have the six-membered ring, and that's called the delta-lactam, alpha, beta, gamma, delta. And one place where this becomes very important is in the production of antibiotics, particularly the penicillin antibiotics, because the penicillin antibiotics all contain a beta-lactam ring. And the structure of one of the penicillins, we have a phenyl ring here, we have a carbamate, here is our beta-lactam, and so this is penicillin 5. And this beta-lactam ring plays an important part in the activity of the penicillin, that it will react with the bacterial enzyme responsible for making the bacterial cell wall. The enzyme will attack this amide bond, thinking that it's a peptide bond in a protein, and then it will attach this whole penicillin group into the active site of the enzyme, preventing that enzyme from working properly. It's also important in antibiotic resistance because other species of bacteria that have become resistant to penicillin antibiotics have enzymes that can break this bond without attaching or without so that the molecule doesn't deactivate the cell wall enzyme responsible for allowing the bacteria to grow. And so this beta-lactam ring as a subject of a lot of research when they were studying how to produce different penicillin antibiotics, because creating such a highly strained ring proved to be fairly difficult, especially when we have a molecule that contains other sensitive groups. So that's our discussion for amides.